So I just kind of gave you a very, very brief introduction to the study of statistics, okay? And again, so why do we study statistics?
To understand the world around us.
And understand the world around us, and I mean, actually, most of the subjects you study is to understand the world around us, right? History and philosophy and all those things generally are there to see help. So what is it that statistics has to offer?
Make conclusions from the data.
Yeah, we're making conclusions basically from limited data. Now, in order for us to even start working in that direction, to make conclusions based on limited data, we have to be able to look at data and be able to describe it. Okay, we have to be able to look at data and see even what this data is saying in the first place. Okay, so we have to be able to look at data and describe it. Okay, so this is where we get into chapter 2. And, so this is all about describing data, right? Otherwise, I mean, if you can't describe the data that you've collected, there's no way you can even make conclusions based on that data, right? So we've got to start here. All right. Well, when we gather data, we can gather data of different kinds. And so you can just imagine, if I said, go around the classroom and I want you to find out, what is the average height of the students in this classroom, and also tell me what proportion of this class is female, okay? How would you go about doing this? How would you gather your data to answer this question?
Count and measure.
Okay, so you might count.
Line everybody up.
Line everybody up. Okay. Okay. Let's say I made the this problem a little bit more complicated. I said, okay, well, find out the average height of the females and the average height of the males. Okay. Well, if you're going to gather this data, what program would you use on your computer, or how would you set up your paper?
Excel.
Okay, you'd use Excel and you'd set up some kind of table, right? Alright. And how would you set up this table?
Female,
Female, male, okay. What do you mean by that? I would make a column for...
Yeah.
Okay. So, that is one possible way, okay? The way I'm going to encourage, or just say, we're going to try to set up data here, is that we're going to set it up where you have column headings, and each row represents a different person or a different case. So each person is going to each row is going to represent a different person. So we're going to, maybe we won't even want the name of the person, okay? And we're going to ask, are you male or female? And well, maybe that's not a nice question to ask. And then we ask, what is your height? All right. And then so student 1, let's say, is Joe. Joe is male and is 5'9". Okay. And student 2, I'm making up names. Is Amber. She is female and she is 5'3". And then we have Barbara, who is female and she is 5'6", or whatever. Okay. So we go on, and this is how our data could be collected. Okay. Each row is a different person. Or sometimes we'll call this a subject, or sometimes we'll call this a case. Each column
Bless you.
each column is a different variable. people might collect data in different ways. But this form of collecting data is generally the most flexible in that you can collect, you can increase the different variables that you are gathering for each person. Okay, so we could just add another column. And so if I said, okay, well, I also want to know, you know, the age of everybody, I can add a column called age and just start listing off, adding that piece of information, okay? And I'm sorry, your name was?
Cynthia.
Cynthia, okay, so Cynthia made a suggestion, and she said, you know, we could make one column for male and one column for female, and then we would list off, you know, how tall each person was. And we'd have 5'9", and we'd have 5'3", and 5'6" okay? So this form works, but if I said, okay, now also find out the age of everybody, you're stuck, okay? It would be very difficult to start adding pieces of age information and things like that in this type of thing, okay? So this really only works if you've got one variable that, you know, so this is kind of limited in the data that can be collected. It's not wrong, but this offers a little bit more flexibility. Okay. Now, when we look at our different variables, we have two big categories of the types of variables that exist. We've got categorical variables. And we have numeric variables. Numeric or quantitative variables. Okay. And these variables can be further subdivided.
Bless you.
But these are the big types that we've got, okay? So categorical variables say our variables belong to a certain category, okay? So each data point belongs to a different category, okay? So it tells us, categorical variables, they tell us which type tells us which type or what kind. What kind for each, for each case. So in our example, sex serves as a categorical variable, or not serves, but sex is a categorical variable. So example, sex, male or female, maybe race, or if we're dealing with anything that could be answered with a yes or no, or this category, that category, those are all categorical variables. On the other hand, we have numeric variables. Okay, numeric variables tell us how much or how many. Okay, so in this case, height is a numeric variable, okay? And numeric variables will always have a number in there, okay? So this will always have a number. number shows up doesn't necessarily mean it's a numeric variable. It always has to answer this question of how much or how many, okay? So height is numeric. Age is often numeric. Salary, income, those types of things. Also numeric. Alright, so if I added more categories, or not categories, more variables to collect, just tell me if this would be numeric or categorical. So let's say I wanted to gather we would ask someone's weight in pounds. That's what?
Numeric.
Numeric. Okay, so this is numeric, clearly. What else? Hair color. Categorical, okay? So it depends what we have, but we'll probably have to list, brown, black, blonde, red, or, maybe we want to split it brown to light brown or dark brown, or whatever we want, okay? Hair color. What if I asked for what zip code someone lived in?
Categorical.
Yeah, zip code is categorical, okay? It's a number, but it doesn't answer the question how much or how many, okay? It doesn't make sense. You would never ask how much zip code do you have, and you would never compare two people and say this person has 20 more zip code than this person, okay? It just doesn't make sense. It makes sense to say this person weighs 20 pounds more than this person, or this person is 3 inches taller than this person, but with zip code, you can't say this person has 20 more zip code than someone else, okay? And with hair color, there's no, you can't even compare colors per se, okay? Unless you wanted to somehow turn it into a number system, and I don't know. I guess now that everything can be digitized in the computer world, right? We can turn categorical things into numbers and numeric things into categories. So age, generally, if I ask how many years old are you, that would be a numeric variable, okay? But the government might look at you as minor, adult, senior citizen, okay? That, I guess senior citizens are also adults, but they might put you into these categories based on your age, okay? And they say, okay, you are 17 years old, you don't get to vote. You're 18 years old, you get to vote, okay? You're 70 years old, you get Social Security, things like that, okay? So those are categorical variables based on, basically, there's an underlying numeric variable that would turn into a categorical variable. So that also exists. So depending on how the data is collected and thought of, okay? Among our numeric variables, those can be, the book talks about the terms discrete and continuous, okay? Discrete meaning you can only take on certain values as an answer. So how many children do you have? People will only answer that with a whole number answer. On the other hand, how tall are you? If we had a very accurate tool to measure someone's height, we can get, somebody could be 5'5.03" inches, and someone else could be 5'5.08" inches, and they would have different heights and things like that. If we are going to display or summarize, displaying and summarizing categorical data, okay, so let's say we go through our class and we list off, you know, all 30 students or however many there are, okay? So I've got, so just imagine I've got a table. I would have 30 rows, one for each student. So if I want to summarize for one variable, for sex, okay? For the variable I would create something called a frequency table, okay? And this would say sex, count, male, female, okay? This would be frequency table. And I would say, well, there's a total of 30 people. 22 are female, and 8 are male. Something like that. Okay. Sometimes we add another column, and we will say proportion or percentage. And so we do 8 divided by 30. 26.7%, okay, or 0.267, which means this is going to be 0.733. Okay. And that's our frequency table. If it includes proportions, we'll call this a relative frequency table. And if we wanted to display this, we would have to draw this somehow. Alright, and I would say this column represents male, and female, okay? And over here, you know, label this 0.20, 0.40, 0.60, did I do this wrong? I don't know. Okay. Might not be the most accurate thing ever, but oh well. Okay, and this could also be the count. 10, 20, 30, or something like that. Here, I hope your picture looks better than mine. Okay? And this is, we call this a bar chart. Alright, a key thing about the bar chart is that I could rearrange the order of the bars, and it would be just as valid. Okay, so I could put the female column over here, and the male column over here, and you know, as long as I've labeled the axes correctly, this is equally valid. And I could have a whole bunch of different categories. All right, so let's say we didn't look at sex, but we looked at hair color. Okay, and I could list off all of the different hair colors that exist in the classroom, and I don't have to put them in a particular order. Okay, across the I would create a bar, one for each hair color, and maybe I have blonde, brown, black, red, okay? And we would have different different bars here, okay? Something, whatever. I could rearrange all of these bars, and they'd all be equally valid, okay? And that's something about the bar chart. On the other hand, if I'm dealing with a numeric variable, the way I summarize data and look at them is also very different. Okay, so a frequency table and bar charts, this is for categorical data. Okay. Now let's talk about displaying and summarizing. So if we've got numeric data, now I'm dealing with something such as, you know, the height column, or the weight column, or the age column in our data table. Okay. So, alright, so let's just imagine we're just looking at this the age column. Again, I've got 30 rows. 30 different numbers here, and maybe my numbers are like, I got 26 and 31 and 38 and 25 and 19 and 22 or whatever. Okay, I've got 30 different numbers here. Okay, so here I only have 6 numbers so far, but I would have a total of 30 numbers. One tool that I could use to display it is the dot plot. And a dot plot starts off with a number line. So we first have to create the number line. So let's say so I've got a number line, and what I'm doing is I'm going to put a dot for each point, for each number that shows up in my data set. So I put a dot at 26, I put a dot at 31, a dot at 38, a dot at 25, and 19, and 22. Okay, and I would do this for each point that I have. So at the end, when I'm done with this, how many dots am I going to have up here?
30.
30 dots, one for each person. Okay. Now, if somebody else was 25, okay, we would just put the dot right above the other one. Okay, and so you'd start stacking these dots on top of each other. Okay, and dot plots are great if you don't have too many data points. Okay, they're great if you got 20 is usually a good number. 30 is okay. Once you're getting above 30, a dot plot starts to get a little bit muddled with too many data points. Okay, but a dot plot gives you a good idea of just kind of where your data lie. You get an idea of kind of where the center is, how much spread there exists, and things like that. Okay, so So this is a dot plot that I have for okay, so this is just maybe seven students from my XL13 class. Okay, I teach another class, XL10. Most of my students there are still in junior college, and they're looking to transfer, and XL10 fulfills some kind of math requirement. So that changes the students that are in that class. So let me just say, so this is for XL13. So maybe I have a listing of numbers of ages again. Let's say for my XL10 class, and let me just list off maybe some ages of some of the typical students there, and probably 19, 20, 21, 19. Okay, so here I've got five students from that class. And if I look at the numbers there, so I'm going to just put open circles to represent these numbers. And if I create a dot plot there, I could add more. You know, let's say I got another, like someone at 23. Okay. So here I've got 6 data points, and up there I also have, well, I've got 7 data points. But we can see very quickly, right away, by looking at the 2 dot plots, we can see, you know, where's the center of this dot plot? You know, somewhere around here, here-ish, okay? And over here, where's the center? Somewhere around here, around 20-ish, okay? We can also see there's a lot more spread in this classroom than down here, okay? So we can get an idea of, from the dot plot, we can get an idea of the center and the spread, and even maybe the shape. Okay. Now I haven't really talked about shape, but you know, I'm just kind of introducing some of these concepts to you, and we'll get more into it in a moment here. But here we can see, you know, by looking at the numbers from 2 different classes, and just again at the ages, we can see, you know, the demographics of our class are different between the 2 groups here. Okay. So the dot plot serves as a nice way to display our data. Okay. If we get more than 30 or so dots, okay, the dot plot can get a little cluttered, okay, and so for tools that handle a little bit more data, one of our tools that we use to display it is a histogram. Okay. So a histogram looks kind of like a dot plot, except we don't put any dots, and we put bars up on the histogram. Okay, and to some degree, a histogram takes a numeric variable and kind of creates little mini categories. Okay, categories based on the values, and we call these bins. Okay, so we make bins for our histogram. Okay, now the bins could be individual values. Okay, so we could have a bin, and we could say how many people are age 19, and we could say one person is age 19, and we say how many people are age 20, and we say, oh, there's 2 people who are age 20, and how many people are age 21, and we say 0 people, and say how many are age 22? 3 and 23, maybe 4 and age 25. There's another 4, and so on and so forth. Okay, and we create bins for each of these things, and we say, you know, how many people fit in that bin. Okay, and technically, when we say 19, at least this is how ages work in life. It's that you say you are 19 until if you are 19 years old and 364 days, you're still 19, and then the next day you turn 20. Okay, so technically you're like 19.99 years old, but we say you're just 19. So, but really this is 19 through 19.99 years old, right? And 20, when someone says I'm 20 years old, that's really they're between 20 and 20.99 years old, and I don't know, at midnight you turn 21, okay? And then you can go into the bar and drink. But that's how the histogram works. Sometimes if there's too many, okay, like if we, you know, this might work for a class, but if you tried to make a histogram with individual ages for, I don't know, people at a baseball game where you've got, you know, 25,000 people in the stadium, and you might have a wide range of ages, you know, from age 0 to age 80 years old, or whoever the oldest person in the stadium is, you'd have 80-something bins, right? That's too many bins. We're trying to decrease clutter, so you can also create bins with a larger range. And you could say, oh, okay, we're going to go from age 0 to 9.99 years old, and age 10 to 19.99, and age 20 to 29.99, et cetera, et cetera, et cetera. Okay? And you create bins. So if we did this for our classroom, we would have, you know, using the same data here. 0 people between 0 and 9, and then maybe I got one person who's 19, and I didn't finish this out, but we know we have at least 11, 12, 13. So maybe we've got 19 people in this thing, and maybe we've got 3 people. You know, whatever. Okay. So so we can create something like this, okay? So the histogram that corresponds to our first bin setup, okay? I would, depending on the textbook that you use, they might have bins centered at the number, or the markers distinguish between the different things. So 19, 20, 21, 22, etc. Okay, I would say I've got one person in between 19 and 20. I've got 2 people between 20 and 21. 0 between 21 and 22, and I've got 3 here. I should put a vertical axis. 1, 2, 3, 4. 3, and then 4 there, 4 there, and the bars go on for this. Okay, so this histogram corresponds to this bin chart setup. Whereas this one, my bars, you know, go from 0 basically to 10, 20, 30, to 40. Okay, and I would have a bar at 1 to basically create some sort of system. And I would create a bar that goes up to 19, and a bar at 3. Something, okay? And this is what the other histogram looks like, okay? So this one has 19, 3, and 1. So people ask questions, well, how wide should I make my bins? And, you know, how do I choose, you know, yeah, how big should I make my bins? Well, the answer is, it depends, and the choice is yours, okay? Basically, if you got something like this, this is probably not enough bins, okay? If your histogram ends up looking like this, you probably don't have enough bins, okay? If you got a whole bunch of these, and if we did this for the entire classroom, we would probably end up with too many bins. So you need to find kind of this sweet spot between the number of bins and, or how wide your bin is going to be for your data. And it's going to differ for each data set. Someone might ask, what's the difference between a histogram and a bar chart? Okay, they look very similar. But the thing is on the bar chart, what did we have across the bottom, our bottom axis?
Variable.
Yeah, we had the categories, the different categories for each variable. Male or female, or hair color, blonde, brown hair, black hair, red hair, whatever other color hair there is, okay? Down here in a histogram, our axis is the number line, okay? And with a bar chart, we said we could rearrange the variables across the bottom, and that was fine, or the categories across the bottom, that was fine. You can't rearrange the numbers on the number line, okay? The number line says the number 3 comes after the number 2, okay? You don't have a choice about where number 3 lies on the number line, okay? So you can't rearrange the columns for a histogram, okay? So the axis, the horizontal axis, is the number line. Can't be rearranged. Histograms, okay. Histograms and dot plots, again, both are used for numeric data. We never use a histogram for categorical data. Bar charts is what we use for categorical data. Okay. So we might see histograms for different sets of data, and the histograms will look different, of course. And we want to be able to talk about the shape of the histogram, okay? The shape of the histogram, and what do those shapes actually mean, okay? The shape of the histogram, or the shape of the distribution. Okay? Because a histogram is just a pictorial representation of the numbers in our data, right? And when we talk about the numbers in the data, we're actually saying, you know, what is the distribution of data there, okay? So just remember, it's simply a picture representation of data. And what we really want to know is, what does our data look like? Okay, so if we looked at the histogram of people's heights, okay, let's say we just look at the heights of women in the United States. Our histogram would look something like this. Okay, this is a possible histogram for the heights of women in the United States. U.S. women. I always have trouble pronouncing women. It's hard for some reason. It's an I sound. It blows my mind. Okay. And the center is around 5'5", 5'4". Okay, so we'll just say the center's at 64 inches. Okay, and some women are taller and some women are shorter. And so we have this. Okay, but let's just say 5'4" is the most common height, and yeah, we have women who are taller than 5'4", but the farther away from 5'4", so I don't know, this is 5'5", 5'6", 5'7", you know, actually this histogram's not very good, but the farther you are away from 5'4", the fewer we have. Okay, so this might be, you know, women who are 6 feet tall. Okay, all right. Yes, there are women who are 6 feet tall, but they're not very common. Okay, probably about 2 or 3, you know, maybe 2% of women are 6 feet tall or taller. Okay, maybe not even that high. Okay, and on the other hand, if we go in the other direction, yeah, you know, we have women who are 4'10" or shorter or things like that. Actually, you know, maybe 4'8", or what's 56 inches, so that's 4.5 feet. Yes, there are some women who are much shorter, but they aren't as common. Okay, and around the middle is the most common heights of women, and these are the so we see this more frequently. That's what the high bar represents. So these heights are most frequent, whereas these ones are less frequent, and these ones are less frequent. Okay, we would I could also just summarize this with a curve that looks like this. This is pretty much saying the same thing here, and we would call this symmetric. We would say the shape of this thing is symmetric, and we would also say it's unimodal. Okay. Symmetric refers to the fact that if I go 8 inches above the center, I don't have very many, and if I go 8 inches below the center, I have just about as few people as there. Okay, and if I go 3 inches above the center and 3 inches below the center, I have just about as many who are 3 inches above as I do 3 inches below. So that's the idea of symmetric. Unimodal says we have one height that's the most common. Okay, this is the most common, and it's kind of centered around there. So basically one peak. Unimodal means one peak. All right. Maybe I have a histogram, and we go around and we ask, how many teeth do you have? Okay. All right. So if you haven't had your wisdom teeth removed, how many teeth will you have? You will have 32, right? I think this is the number. Any future dentists? Okay. But then a lot of people get their teeth removed and things like that. And so we probably have a bar at 32. Usually people don't get just one tooth removed or something like that. Maybe they'll get 2, and so maybe we'll have a few people at 30, and then 28 is going to be pretty common, and some people, yeah, maybe they lose a tooth or something. Anyway, you're going to have a distribution that looks something like this, okay? And actually, where people lose teeth and things go on. Okay, so this might not be the best example. But this could be summarized kind of with an illustration like this, right? This type of curve. This, we would say this shape, this is skewed, okay? And we, in particular, when we say it is skewed left. Okay. And what does it mean to have this type of shape? Okay. It means most of your points are in some zone here. Okay. So most points are around here. But you've got some people or some points that are much smaller, okay? Much smaller. But no one, okay, not very many, but yes, you do have some people where the number of teeth is much smaller than everybody else's number of teeth, okay? But on the other hand, if you try to go in that direction this way, there's no one over here. No one much higher. So yeah, most people have something between 26 and 32 teeth-ish, somewhere in that zone. But yeah, you know what? Some people lose a bunch of their teeth, and maybe they have, you know, a lot of them are removed, and so they have dentures, and maybe they have 8 or 10 of their original teeth. Okay, so that's, you know, about 10 or 12 teeth fewer than what most, maybe like 15 teeth fewer than what the average person has. Okay, but if we go 15 teeth more than what the average person has, that would be something like 40-something teeth. You don't have anybody with 40-something teeth. Okay, so this is known, we call this skewed left. We've got points that are much smaller, no one much larger. Okay, this is also unimodal because we've got basically one peak. That's the most common.
The skewing that is where the data is not?
It's pointing in that direction. It's where the tail goes, okay? The tail of our distribution. Okay, so something like this, what do we call this? Skew right, exactly. Alright, and if you have trouble remembering, okay, just imagine if I were to cut this out of the board and use it as a weapon. So the Hunger Games came to life here, okay? And I would have to, which side would I attack you with or use to skewer you or stab you? I would use the right-hand side of this thing, okay? So, that's a little bit violent. I'm not a fan of that, but that would be the side that you use. Well, okay, if you're going to cook shish kebabs or some kind of meal on this, which side would you use to skewer your chunks of meat or vegetables? For the vegetarians out there. You would use the right-hand side, okay? You wouldn't try to put your meat on this end. That would not work. Okay. Distributions that might be skewed right, okay? So height is normally distributed, but weight, at least in America, is skewed right, okay? And what does that mean? It means most people are in this kind of this zone here. We have some people who are much heavier than the rest of the population. Not very many, but we have some people who are much heavier. But if you try to go that distance far below, you don't have anybody. Okay, so I don't know. The average weight of someone in America is like 160, 170 pounds, something like that. Okay, and you know, on TV they'll sometimes showcase somebody who's like 400 pounds or something like that, right? So someone who's 400 pounds is basically 230 pounds above average. If average is 170 pounds, 400 pounds is 230 pounds above average. If I try to go 230 pounds below average, that would take me to negative 60 pounds, okay? Nobody weighs negative 60 pounds. So weight would be skewed right, okay? And then there's all sorts of things that can be skewed or things like that. Okay, all of these are unimodal, meaning we've got one peak. Sometimes we have data that looks like this. This would be bimodal. Okay, we can also have, these are both bimodal. Okay, and usually we just go with a 1, 2, or many. If you got more than 2 peaks, we would say this is multimodal. All right, what might be bimodal? Okay, remember this is what kind of what kind of variable are we dealing with? Numeric. Okay, so we can't have any kind of categorical variable here. Okay, so only numeric variables can be described as unimodal or bimodal, can be described as symmetric or skewed left or skewed right. Okay, something that might be bimodal is basically testosterone concentration in humans. Okay, so if we drew blood or something, or we had you spit in a cup and we measured how much testosterone your body produces, okay, we will probably see very much a bimodal distribution. Okay, we will see a kind of a zone. I don't know how testosterone is measured. It's probably like milliliters per liter or something like that, right? Or I don't know, milligrams per liter of something or something. Okay, some concentration thing. And so we would have, this would kind of be the amount of testosterone the average male produces, okay? And this would be maybe the testosterone that the average female produces, okay? Some men produce more testosterone than other men. Some men produce less testosterone than other men, okay? And some women produce more testosterone than other women, and other women produce less testosterone, whatever. Everybody also produces some amount of testosterone in their body. And actually, testosterone probably looks more, the distribution of testosterone probably looks more like this, where you've got a very distinct break, where you have very few people in kind of this middle zone, okay? And this is actually how the Olympics now classify who is male and female, okay, in their competitions. Okay, they drew some arbitrary line, and they said if your testosterone level is this, you have to compete as a male, and if it's less than this, you compete as a female. Okay, it's you'd think whether someone was male or female would be a simple, I don't know about simple, but would be more straightforward, but yeah, there was that runner from South Africa, Caster Semenya. I don't know if you remember this controversy.
Mm-hmm.
Poor girl. She she did really well, and then the other athletes said, she's not a girl, she's actually a man, and so well, anyway, they measured her testosterone levels, and she fell into the normal women range, and so that was like, no, I'm a woman, and you guys are terrible people. Okay. But yeah, that's what it comes down to. Okay, so anyway, sometimes whenever someone talks about a distribution of things, just think in your head, would that be skewed left or right or symmetric? These are things that we don't generally think about as we go. But all of this is to show that whenever we gather data, numeric or whatever, there's variation. Okay, variation exists in our data. Okay, so. And a histogram gives us a picture of where our data lies. So it gives us a picture of kind of the location, and it gives us a picture of the spread or the variation. Okay, so histograms and dot plots. Where our data lays, where our data is. And so either location or center. And also gives us a picture of our variation or the spread. So we have an idea, you know, are the numbers similar to each other or are they vastly different from one another? Okay? And this and the shape. So these visual tools are great. Okay, so all of these things, you know, these pictures, they're great, okay? But sometimes, if you couldn't use pictures, right? If you had to describe a distribution or where, you know, your data, if you want to summarize your data without listing off all of the points to someone over the phone, you've got to use words, okay? And pictures won't always work. So so we have numerical summaries too, okay? So for numeric data, we have numeric summaries. We actually had numeric summaries for categorical data. And what were those numeric summaries? We talked about it not too long ago. We counted, okay? We said this is how many fit in this category. That's a numeric summary of a category. And we also use the proportion, okay? And we said, okay, we have 22 females in this class. That represents, you know, 70% of the class is female, or something like that, okay? So those are numeric summaries for categorical data. Here we're going to look at numeric summaries for numeric data, okay? So we have numeric summaries for the center. For location. So in particular, we have the center, which can be summarized using the mean or the median, okay? Okay, the mean, this is what we typically think of when we hear the word average. Okay. This is the balancing point of our data. Okay. So just imagine I've got a dot plot. Okay, so all dot plots, we've got a number line and I've got dots on this number line, right? Something like that. So if I were to calculate the mean of this data, the mean of the data is where I would put the little triangle on my seesaw, the fulcrum, so that this thing is in balance, okay? The location of this thing is the mean. I don't know. Would that be balanced there? Ish. I don't know. Okay, wherever it would be balanced, that is the mean. I don't know, maybe it would tip this way. Okay, but wherever it's balanced, that's the mean, okay? The median, on the other hand, this is the middle point. This is the point where half of your data points are larger and half are smaller. This is the middle point. So I think everybody already knows how to calculate the mean. Okay, the symbol that we use for mean when we're talking about a sample of data, okay, the mean for a sample of data, or our sample mean, the symbol we use there is y bar or x bar, okay? Our textbook uses y bar, other textbooks use x bar, okay, no big deal. And the way we calculate it is we add up all of our data points and we divide by how many data points we have. Okay, and that's what this summary says, or this formula says. Add up all of your data points. This symbol right here, which looks like a E or a sideways M, it's actually the Greek letter sigma. Sigma is the Greek version of S for sum. Okay, so you add up the data, add up all points, and then divide by the number of points. That is going to give you the mean. It's going to give you the balancing point in our data. Alright, so that's, I'm assuming, is familiar for all of you guys. The median, again, is the middle point in our data. Okay, so let's just say I've got a whole bunch of data points. Let me just find some numbers here. Just joking about something. So here I've got 14 data points. So the median is going to be the place where half of my data points are larger and half are smaller, okay? So the first thing here is I've ordered them from smallest to largest, okay? So notice that our data points are in order from smallest to largest. To do this, it's not going to work, right? So if you want to say, I want to split the classroom in half and put the shorter people in one group and the taller people in another group, you want to just say, okay, everybody stand by the wall and this half is in the short group and this half is in the tall group. You first have to say, okay, everybody up against the wall in order of height, and then you can say, aha, This is the point, and half of you are shorter than this, and half of you are taller than this. Okay? That's what we're going to do when we do the median. So here, I have 14 data points. N is equal to 14. So the median is going to be the spot where I've got 7 numbers that are smaller and 7 numbers that are larger. Now, a way that we can find this is it's the median is the number in the n plus 1 over 2 position. Okay, so what does that mean? Okay, well, if I do n plus 1 over 2, 14 plus 1 over 2 is 15 over 2, 7.5. It's the number in the 7.5 position. So, I'm going to just count. I'm going to go 1, 2, 3, 4, 5, 6, 7. So this is my 7th place number, and this is my 8th place number. Okay? So the 7.5 number is the number that's in between this number and this number. So the median is right here.
Bless you.
So what is my median? It's going to be the number that's halfway between 9 and 10. So, I mean, we can intuitively say that's 9.5. But if you aren't sure, your median is going to be, you do 9 plus 10 divided by 2. Just take the average of the two middle numbers, and you get 19 over 2, or 9.5. This is my median. If I had another number here, 30, I would have 15 numbers. 15 plus 1 is 16 over 2, 8. So my median would be the 8th place number, which is 10. Okay? But I don't have the number 30 there. Okay? So that's my median. Other numbers, okay, so numeric summaries for location. So the center can be summarized with the mean or the median. Other numbers that we can use that summarize location are the quartiles, and the min and the max. Okay, so I've got the min and the max, and then I've got quartile 1, Q1, and Q3. These are the quartiles. Alright, the min and max are straightforward. Min is your smallest data point, your max is your largest data point. So I just erase this thing for the mean before we run out of time. So what's the minimum in this case? 3, and my max is 21. Okay, great. The quartiles are kind of like medians, except the median is the point where half are smaller and half are larger. The quartile, the first quartile, is where 1/4 is smaller and 3/4 are larger. And the third quartile is where 3/4 are smaller. Okay, so the first quartile is where 1/4 of the numbers are smaller, and the third quartile, or Q3, is where 3/4. What's another name for Q4?
Max.
The max. And what about Q2? The median. Okay, yeah. So Q2 is equal to the median, and Q4 is the max. I guess you could have Q0, but I've never heard anyone call it that. Okay, and Q1 is where 1/4 is smaller. Okay. Now, different textbooks will describe different ways of finding Q1, and if you use Excel to find the first quartile, it'll give you a different thing. Okay? The way we're going to find quartiles is the way our textbook talks about it, which is basically we find the median, which splits our data into half larger and half smaller, and then we're going to find the median of each half. Okay? So once I found the median, I've got 7 numbers that are smaller than it, and I've got 7 that are larger than it. So with this 7, I'm going to find the median of these 7 numbers. And what's that going to be? It's this number right here. This is the median of the 7, and this is going to be Q1. Okay, and if you weren't sure about that, you can do, it's the number in the n plus 1 over 2th position. So I do 7 plus 1 over 2, it's the fourth place number. And I go 1, 2, 3, 4, and I get 7. That's Q1. I do the same thing over here, and I go 1, 2, 3, 4, and this is Q3. Okay, so those are numeric summaries that we have for position. Okay, now we can talk about numeric summaries that describe the amount of variation or spread that exists in our numbers. So again, all of this, just so we don't get lost in all of the stuff that we're doing, this is all just so we can describe data, okay? Because we want to, our big picture is we want to make conclusions based on limited data, but first we got to be able to describe our data first. So numeric summaries for spread, I'm still talking about a numeric variable, okay? Spread or variation. How different are the numbers from each other? We have the range, and we have the IQR, which is the interquartile range. Just a fancy name. And we have the standard deviation. I'm going to run out of time. Okay, the range is easy. You take the largest number, your max, and you subtract your minimum. Okay, max minus minimum, that's going to give you the range. So here I do 21 minus 3. I have a range of 18. Okay. By the way, nobody asked me what these numbers are. Okay, these this is from the textbook. This is radish growth length. Okay, so we planted some radish seeds in a planter, and we let them sit for a few days or something, and then we measured how tall the radish seeds grew in millimeters. Okay, so some only grew 3 millimeters, and then our radish Superman grew 20 millimeters and 21 millimeters. Okay, two super radish. Okay, the interquartile range, or the IQR, is the range between quartiles. So it's Q3 minus Q1. So I do 10 minus 7. My interquartile range is 3. And we'll talk about the standard deviation in a moment. Okay. So this gives me an idea of how spread out are. This also, what percentage of the data is within the interquartile range? 50%, right? Because Q1 represents the 25th percentile, or where 1/4 is smaller. Q3 represents where 3/4 are smaller. So basically I have 2/4 in between Q1 and Q3. So I've got 50% of the data. The middle 50% is within the IQR. Okay. So this gives us an idea. Yeah, when you look at all of the radish, how much the radish seeds grew, there seems to be a wide range. Okay, some grew a tiny bit, some grew a lot more. But when you're looking at kind of like the typical radish seed, how much did they grow? There wasn't a whole lot of variation. The bottom 25th percentile, the bottom quarter grew 7 millimeters, and then the top quarter, or the 75th percentile, grew 10 millimeters. So in this middle zone, like of middle, whatever, there wasn't a whole lot, just 3 millimeters difference separated the top 25% from the bottom 25%. That's what the IQR gives us an idea of okay? Ooh. I'm going to run out of time to talk about the standard deviation, okay? I've created a little video that goes into the calculation of the standard deviation, okay? But the concept behind these are all just number summaries that talk about the spread, okay? And what the overall concept behind the spread is, are the numbers very different from one another, or are they very similar to one another, okay? So the spread for my XL10 class's age range is a lot smaller, okay? A lot of the students are all kind of in the same age group, where in this classroom, there's a little bit more spread.